Sir, good morning.
Good morning, sir. Good morning.
Just 5 minutes will start, okay? As
Okay, okay, sir.
Shailesh
Okay.
sir was a different session, so we have to
Okay,
start.
okay. Okay.
I have made you co-host, so whenever you feel you can share the screen as well.
Yeah, yeah. So students from various other colleges are also participating.
I guess so. Shailesh sir has more idea.
Because initially what I was told that there is a university in Dehradun, Devbhoomi
Uh-huh.
University. Are they participating?
Now they're getting admitted. So let's
Sir,
wait for
you
five
can
minutes.
admit people, sir. Instead of me admitting, you can admit people because that will be better.
Shailesh sir,
जी सर, जी सर.
morning.
Good
Girijan sir
morning,
is
sir.
already connected.
Giriraj sir, good morning, sir.
Good morning, sir. Good morning. Very good morning.
जी sir.
So just let me know when we need to start.
I think just बच्चे जुड़ जाएं थोड़ा सा 2-5 मिनट बाद फिर अपन स्टार्ट कर दें. मैं एक बार ग्रुप में भी मैसेज करवा देता हूँ सभी को.
Okay.
जी. Rahul sir, I think we can start.
Yes, sir. So Girijan sir, can we start?
Yeah, yes, sir. We can start now. It's already 10:35.
Yes, yes, yes. Okay. So welcome everyone on this session. A very important topic related to the spectrophotometry, and we have an expert speaker, Mr. R. Girijan, who is a product consultant, Toshpin Analytical Private Limited, Mumbai. Uh, a very experienced person, and we are blessed to have him with us on this session in association with the Ennoble Academic Society and Millennium College of Pharmacy, Millennium College of Pharmacy and Science, and the entire Millennium Group. We are thankful to you, sir. We have Dr. Shailesh Gupta with us. We have Dr. Ashish Jain and the other dignitaries of different colleges, students of different colleges of Millennium College of Pharmacy, College of Pharmacy and Science, and the faculty members. So, with these words, I would request Girijan sir to please take over the session and enlighten all the students with the words of wisdom. Over to you, sir.
Thank you, sir. Thank you for the introduction and welcome. A very good morning to all the participants. I'm happy to be with you all today this morning. And if I remember, this is my second session with the Ennoble Academic Society. I think I conducted one session, I think 2 to 3 months back.
Yes, sir.
So
Yes.
I think in the month of May, I suppose, if I remember correctly. So I know all the participants are pharmacy students, B Pharm students and M Pharm students. So when we conduct this type of program, especially for pharmacy students, is a very important topic we are going to discuss today. And in pharmaceutical industry, pharmaceutical analysis assumes a lot of importance, especially in routine quality control, research and development, new drug discovery, process control. There are a lot of areas where we carry out different types of analysis. Very, very important analysis we carry out. And we use different types of techniques also. We use different types of spectroscopy techniques. We use different types of chromatography techniques. So many different techniques are available today in pharmaceutical industry, and they're all very, very important. So when all the students see, now you are learning all this in the college, in the university, and one day you are going to come out, you are going to enter the corporate world. Many of you may be going for higher studies. So you will definitely be exposed to different types of techniques when you enter the corporate world. And then there you are expected to handle all these techniques, you are expected to use all these techniques very effectively, very efficiently. So the base work for all this should be done in the university, in the college. And I am sure all of you are studying all these techniques, and the topic we are going to discuss today, briefly discuss today, it's a very, very simple technique, but yet is a very powerful technique. And I am 100% sure all the students must be knowing about this. Our topic today is UV visible spectrophotometer. Very simple spectrophotometric technique, which is widely used in industry as well as academic institutions. And when you use a technique, I always tell the students, when you use a certain technique for a certain type of analysis, there are two aspects. One, even if I get a 12th standard student, I give him some basic training. He or she may be able to use it and give me the result. But the person may not be knowing actually what is happening. He is just following a certain SOP, a set of SOP prepared by somebody else, just following the SOP 1, 2, 3, 4 steps, taking out the result. But if you know the technique well, how it works, what are the underlying principles, then probably you'll be able to do a much better job. You may be able to use your own logical thinking, and you may be able to do a better troubleshooting. And that is the importance of learning the technique before you start using it for a certain analysis. So these type of platforms, these type of programs will give the students to understand the basic principles, the basic techniques that are used in every analytical technique, so that you will be able to effectively and efficiently use it in your, maybe in your higher studies, or when you are going for a corporate job, or you are for all those. So with this, I think I will, without taking too much of time, I will be directly going to the topic. And I thought to again, it's a very simple topic which we are going to discuss: UV visible spectrophotometry technique. It is a it is a spectrophotometry technique. Essentially, okay, now I will start sharing my screen. Okay. Can all of you see the can all of you see the slide? Hello, can all of you see the slide? The slide is visible. Please tell me.
Yes, sir, visible.
Okay. It is moving now. It is moving. Slides are moving also.
Yes.
Okay. Okay. So when we talk about analytical technique, it's all coming under analytical chemistry. And what is analytical chemistry? It is nothing but analytical chemistry deals with different types of analysis like separation, identification, and quantification of different types of samples. So analytical chemistry is a very vast field. We use different types of techniques for different types of analysis. Some of the analysis will be qualitative in nature. Some of the analysis will be quantitative in nature. And analytical chemistry also utilizes classical wet chemistry methods. So all the students know there are a lot of very powerful wet chemistry methods available. And we are not underestimating the power of wet chemistry methods. They are also equally important. So we have classical wet chemistry method and modern instrumental methods. Both are required. Both have got their own advantages also. So instrumental methods will include different types of chromatography separation methods, spectroscopy methods, and there are a lot of other material characterization techniques. So many different types of techniques are available to you for different types of analysis, maybe for a routine quality control of a drug product, maybe for a product characterization, for a development of a new molecule. There are so many avenues where we can use these type of analytical techniques. Especially when you talk about spectroscopy techniques by and large can be broadly divided two types, molecular spectroscopy and atomic spectroscopy. The bifurcation is done on the basis of whether the changes are taking place at the molecular level or whether it is taking place at the atomic level. And even before discussing this, what is all in spectroscopy, what is that we are going to study? When a sample is subjected to a certain type of radiation, some changes are going to take place in the sample. And these changes are all what we are going to study using a specific spectroscopy technique. Now it is broadly divided into molecular spectroscopy and atomic spectroscopy. In atomic spectroscopy, we have different types, again, atomic absorption spectroscopy. We have inductively coupled plasma emission, inductively coupled plasma connected to mass spectrometry with ICP-MS. And in molecular spectroscopy, again, we have different types. For example, we have nuclear magnetic resonance, we have Raman, we have UV visible, we have Fourier transform, infrared. All these are coming under molecular spectroscopy. So what we are going to discuss today is UV visible spectroscopy technique. So identification techniques is coming under the heading identification techniques. And there are so many different identification techniques. UV visible spectrophotometer is number one. That's stopping the list. We have infrared, we have atomic absorption, we inductively coupled plasma, fluorescent spectrophotometry. There are different types of techniques available coming under this family, identification techniques. So before we discuss any spectroscopy technique, this is the starting slide, electromagnetic spectrum. And I hope all of you know what is electromagnetic spectrum. Today we have different types of energies available, different types of radiations available. Even you look out of the room, you see sunlight, that's a type of radiation. And each type of radiation has got two fundamental characteristics. One is the wavelength range, and second one is the energy content. Both these will change, can vary, can differ from radiation to radiation. So that means different radiations will be having different energy contents, and also they will be having different wavelength regions. So we try to arrange all these different types of radiations in a very sequential manner. It's a very orderly manner. We get what is called electromagnetic spectrum. So what you see is a part of the electromagnetic spectrum and how they are arranged. They're arranged in the order of decreasing energy. That means if you look at the slide and if you travel from the left-hand side to the right-hand side, if you move from left to right, energy is coming down, energy is decreasing. And everyone knows energy and wavelength have got a inverse relation. That means when the energy is decreasing, the wavelength is increasing. So you can say all these radiations are arranged in the decreasing order of energy or increasing order of wavelength. So that means on the extreme left-hand side, we have some very, very high energy radiations like X-rays and gamma rays and cosmic rays and all those types of very, very high energy radiations. Whereas on the extreme right-hand side, we have very low energy radiations, like we have radio waves, we have microwaves and so on. And then our UV, visible, infrared, they're all coming in between. They're all members of this family. So if you critically look at infrared, visible and UV is on the left-hand side of visible and visible is on the left-hand side of IR. So that means UV is more powerful compared to visible, energy-wise, is more energy-wise, by energy is more powerful compared to visible, and visible has got more energy compared to infrared. I mean, because that is the decreasing order of energy. Now, what is the UV recording range? I mean, most of the colleges and universities will be definitely having at least one UV spectrophotometer in the lab, especially in the pharmacy college. It's an absolute requirement to have a UV spectrophotometer, at least one UV spectrophotometer in the lab for the students to carry out different types of analysis. And it is a very simple equipment, and it can be used by all the students, maybe postgraduate students or even PhD scholars for their own project work or routine analysis. So, I mean, in between, I may ask very few questions to students. If any student is able to answer, I'll be very happy. Okay, because I will keep on talking and nobody is responding. It becomes very monotonous. So I'll request the students to participate at least once in a while. If I ask a question, somebody can unmute the mic and give me an answer. I will really appreciate that. No, the simple question is, when you are recording a sample in your, suppose tomorrow if you have got a sample, and if you are going to record the spectrum in a UV spectrophotometer, can anyone tell me what is the recording range in a UV visible spectrophotometer? I want the sample to be recorded only in the UV range, not in the visible range. So from what wavelength to what wavelength you will record the spectrum in a UV spectrophotometer in the UV range? Any student can answer this question. It's a very, very simple fundamental question. Anybody? I want a quick answer because I have very limited time. Okay, I have to cover so many things. Can anyone tell me what is the normal UV recording range for a sample? That means from what wavelength to what wavelength you will record the spectrum in a UV spectrophotometer. Am I audible to everyone? Am I audible to everyone? Please answer the question. Hello? 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 Nobody is responding. Nobody is responding. Why?
Yes, sir, you are audible.
Yeah, then can a student tell me, answer my question? What is the recording range for a sample in a UV spectrophotometer? If you don't answer, I will answer. But I expect you to come out with an answer. So it becomes more interactive, it becomes more interesting. Okay. Normally we record the spectrum of a sample in a UV spectrophotometer from 360 nanometer to 190 nanometer. That's a normal recording range, UV recording range. 360 nanometer to 190 nanometer. That's a normal UV range of a sample, for a sample. Okay. Now we can go below 190 also, but you require a different equipment. The normal UV visible spectrophotometer, what is available in your laboratory, cannot go below 190 nanometer. But there are equipments available for that. We can go below 190, but you require a different equipment for that, different UV equipment for that. Normal UV visible spectrophotometer will not go below 190 nanometer. So normally we record the spectrum between 360 nanometer to 190 nanometer. That's a normal recording range. Okay. So that then from 400 to 800 nanometer is the visible region. And above 800 nanometer, you are slowly entering the NIR region. NIR is near infrared region. So most of the UV spectrophotometers that are available in the market today, the total range is starting from 190 nanometer, it can go to 1100 nanometer, 1100 nanometer. That means it is covering UV region, visible region, and part of the NIR region. So that's a normal spectrophotometer range. No wavelength properties of light, or anyone can, I mean, the light, the radiation can get propagated through a medium in the form of a transverse wave. I mean, like you look at the sea, how the water waves are coming, they're going up and coming down, and then that gets propagated. I mean, similarly, the radiation also can get propagated through a medium in the form of a transverse. And when it is having a wave motion, this is what is known as the wave motion, there will be maximum points and there will be minimum points. And the distance between two consecutive maximum points or two consecutive minimum points is called one wavelength, or we normally call it as one lambda. Okay. Now the very fundamental equation, all of you know, C is equal to nu lambda, where C is the speed of light, nu is the frequency, and lambda is the wavelength. So when the light or the energy or the radiation is getting propagated through a medium in the form of a transverse wave, it has got certain fundamental properties. It can undergo transmission, it can undergo absorption, it can undergo refraction, and also it can get reflected from a surface. So these are some of the properties associated with this. Now, what happens when light strikes a molecule? Now you have a sample, you have got pharmaceutical drug. That is your sample. It's a chemical molecule. So when a certain type of light is going to strike the molecule, what happens? That is what you are going to study using a suitable spectrophotometric technique. And the incoming radiation can be of two different types, whether it can be a low energy radiation or it can be a high energy radiation. If a low energy radiation is falling on the sample, it can create two different types of changes or transitions, what we normally call as transitions. It can induce vibrational transitions, where the chemical bonds in the molecule can vibrate. That is normally what we study by infrared spectrophotometry. And it can also induce rotational transitions. The chemical bonds can rotate about an axis. Similarly, when a high energy radiation is coming and falling on a sample, it is going to induce a different type of change. That is what is known as electronic transition. Now, UV being a high energy radiation compared to IR, UV is a very powerful radiation, it's a high energy radiation. So when your sample is getting subjected to UV radiation, it is going to induce an electronic transition in the molecule. That is all. That's only transition that is going to be induced by UV. It's an electronic transition that is going to take place in the sample molecule. And we need to understand what is an electronic transition. Okay. So different types of transitions are possible when different types of radiations are going to come and fall on the molecule. So now, for example, if you look at that atomic structure, there are different energy levels. Now, when any sample at a normal condition has got certain amount of energy associated with the sample, which we normally call as the ground state energy or the ground level energy, it is represented by E0. E0 is the ground state energy. That is the amount of the quantum of energy associated with the sample and normal conditions. Then if it is, then there are other higher energy levels like from E1, then E2, these are all higher energy levels. Similarly, between two energy levels like E0 and E1. Consider E0 is the ground level, E1 is a higher level, which normally called a excited level. So between E0 and E1, there are different, these are called energy levels, E1, E0, E1. These are called electronic levels, different electronic levels. And between two electronic levels like E0 and E1, you have different vibrational levels like V0, V1, V2. These are vibrational levels. And between two vibrational levels like V0 and 1, there are different rotational levels. Different rotational levels. Okay, now rotational transitions are normally studied by microwave spectroscopy, and they involve the lowest energy, very, very low energy transitions. And if you consider vibrational transitions, which are studied by infrared spectroscopy, their energy content is slightly more than rotational transition. And then if you consider electronic transition that is taking place in UV, that's the highest energy transition, very high energy transition, electronic level. So electronic transitions involve very high energy, vibrational transitions involve lower energy, and rotational transitions will involve very, very low energy content. So rotational transition is studied by microwave spectroscopy, vibrational transition is studied by infrared spectroscopy, and electronic transitions that are taking place when your sample is subjected to UV radiation. So what is electronic transitions? Again, you know there is a ground state energy for every sample at normal conditions. Ground state energy or ground level energy is zero. And now this sample is subjected to UV radiation. It's a very powerful radiation. Now, depending upon the type of sample, a certain amount of energy from the incoming radiation will be absorbed by the sample. Then what will happen? The total energy content of the sample will increase because it has already got some ground energy, that is E0. Now it has received some additional energy from the incoming radiation. So what will happen? The total energy content will increase from a lower level to a higher level. That means there is going to be an elevation of the energy level from E0 level to E1 level. E1 level is a higher level, which we normally call an excited state of energy. So the energy content is increased from E0 to E1. So the difference between these two levels, E1 minus E0, I can write it as delta E or H nu. That is the quantum of energy absorbed by the sample from the incoming radiation. But why we call it electronic transition? So when, and you know the atomic structure, there is a central nucleus and a lot of electrons are orbiting around the nucleus in different electronic orbitals. So when the sample is subject to UV radiation, an electron from the outermost orbital is getting elevated to a higher energy level. And because of that, we call it as an electronic transition. And for electronic transition to take place, the incoming radiation has to be very powerful. UV radiation can cause it, whereas IR cannot, because IR is a low energy radiation, so it cannot induce an electronic transition, but it induces certain other transitions like vibrational transitions, which are taking place in the molecule. Now, what is the absorbing species in UV visible? Electronic transitions can involve your organic compounds. That means all your pharmaceutical compounds can fall under this category. It can involve inorganic compounds, many times complexes, all those. So the basic process, your molecule is, radiation is coming and falling on your molecule, M plus H nu. H nu is the energy. Then what will happen? This molecule will absorb energy and it will go to an excited state. M will get converted to M star. M is the ground level and M star is the excited level. But then the excited level has got a very short life, approximately 10 to the power of -8 to 10 to the power of -9 seconds. And it will come back to the ground state. M star will come back to M, that is the ground state, releasing the amount of energy absorbed. It can come out in the form of heat, it can come out in the form of fluorescence, it can come out in the form of phosphorescence, all these are possible. Or a totally different reaction can take place when the M star, instead of coming back to the original form, the base level, it can get converted to a totally new entity. M star can get converted to N. N is a totally new entity. It is nothing but a photochemical reaction. Okay. Now, all the students know, you must have studied in your curriculum. I mean, if you consider the atomic structure, different or the atomic orbitals. These are called sigma orbital, pi orbital, n orbital, sigma star, and pi star. Now, sigma, pi, and n, they are all called occupied levels. Their electrons are already present, and pi star and sigma star are unoccupied level. So there can be always a transition from an occupied level to a unoccupied level. That means there can be transitions like from an electron can go from a sigma level to sigma star level. That is called a sigma star transition. It involves the maximum amount of energy. And these type of transitions can take place in saturated hydrocarbons, alkanes, or paraffins, what we call. I mean, like alkanes, they can undergo sigma to sigma star transition, involves very high amount of energy. It cannot be studied, it cannot be observed in our normal spectrophotometer because they all happen much below 190 nanometer, somewhere around 140 nanometer, 150 nanometer, which cannot be observed in our normal spectrophotometer because our spectrophotometer is starting from 190 nanometers. So we cannot observe these type of transitions. We have equipments for that. Then there can be the transition like from sigma level to it can go to pi star level. Normally we call it sigma pi star transition. And these type of transitions can take place in carbonyl compounds, compounds containing C double bond O groups. Then from pi to pi star transition can take place in unsaturated compounds. Most of the unsaturated compounds, we see a pi to pi star transition, and all these can be observed and studied using our normal UV visible spectrophotometer. Then from non-bond N to sigma star transition can take place. Some other compounds containing oxygen, nitrogen, halogens, they all can undergo these type of transitions, N to sigma star transitions. And N to pi star transitions and also can take place some other carbonyl compounds. So you can see different types of compounds, different types of transitions are taking place, and all these transitions are got varying levels of, varying degrees of energy. So that is what you see, for example, sigma star transition. I told you this can happen, this can take place in saturated hydrocarbons like alkanes, and they're all happening much below, about 150 nanometer or maybe slightly lower than that, so that we cannot observe this in our normal spectrophotometer. Then similarly, pi star transitions, they are all much above 180 nanometer. That means we can study all those type of transitions. Most of the organic compounds and pharmaceutical compounds, we can expect to pi star transitions and saturated compounds. Then N to sigma star transitions like samples containing halogens and sulfur or nitrogen, they all can happen 190 nanometer and upwards. And N to pi star transitions also in some of the carbonyl compounds, it can happen around 300 nanometer. So any transition that is happening above 190 nanometer can be studied, can be observed and studied by a UV visible spectrophotometer that is available. But other things like for alkanes, where sigma star transitions, which are happening much below 190 nanometer, we have equipments because we have to go for certain specialized equipments where we can work with those levels. Okay, now what causes absorption in the UV visible region? So today you got a pharmaceutical drug and you are going to analyze it by UV, provided it is going to absorb UV radiation. Now, if the sample is not going to absorb UV radiation, you simply cannot analyze that sample by UV because it has got zero absorbance. And there are samples which cannot absorb UV radiation. And those type of samples are called UV transparent samples. That means under the range of working range or measuring range of our equipment between 190 and 360 nanometer, these compounds will not absorb. For example, I can give you a very simple example, normal hexane. Normal hexane is a very common solvent that is used in most of the chemical laboratories. If you keep normal hexane in UV spectrophotometer, will you see any absorbance? You will not, because normal hexane being an alkane, the transitions are taking place much below 190 nanometer. You will not be able to observe those type of transitions in the UV spectrophotometer because we can see only 190 and upwards. Below that, we cannot see now. So for this, under the conditions, normal hexane is a transparent sample. So there are samples which are called UV transparent samples. That means we are not able to see any absorption of these type of compounds in the normal UV visible spectrophotometer. But then there are a lot of compounds, lot of pharmaceutical drugs, lot of chemical compounds which are absorbing above 190 nanometers, so that we can conveniently see all those type of transitions and absorbances. So some are the single bonds, many double bonds. Any sample which contain double bond unsaturation will definitely absorb UV radiation in the working range of our equipment. You remember pi star transitions are taking place and we can observe all those. Similarly, conjugated double bonds. Any compound is having unsaturation in the conjugated manner, single double type of attachment. Benzene is an example of that. Benzene is a 6-membered conjugated ring structure, and it is a highly UV absorbing material. Conjugated double bonds. And some metals and inorganic compounds can absorb UV radiation, and samples containing halogen, sulfur, oxygen, those type of samples also can cause absorption. So what is the minimum requirement for a sample to absorb UV radiation? I can ask you a simple question. Again, I expect at least any student to answer this question. What is the requirement for a sample to absorb UV radiation? Can anyone tell me? What is the requirement for a sample to absorb UV radiation? We cannot wait for too much long time, because I have limited amount of time. I am repeating, I have limited amount of time. So anyone want to quickly answer, you are welcome. No problem. What is the requirement for a sample to absorb UV radiation? Any answer coming from the students? Okay, I will tell you. When you have a UV spectrophotometer in your lab, so many different compounds are coming to a sample to your lab. Whether you can analyze all these compounds? Answer is no. There are certain compounds, I told you just now, there are certain compounds which are called UV transparent samples. That means they cannot be analyzed by UV spectrophotometer because they don't absorb in the measuring range of our equipment. So then what type of compounds can be measured? It's any sample which contains a chromophore. The minimum requirement is the compound, the molecule has to contain at least one chromophore. What's the chromophore? Chromophore can be a functional group. So molecules having unsaturated bonds or free non-bonding electrons that can absorb radiation of relatively low energy are called chromophores. Why I am specifically telling relatively low energy? Because I want the compound to absorb above 190 nanometer. If it goes below 190 nanometer, it is going to the high energy side, and our instrument cannot see those type of transitions. We cannot see the absorbance because of those type of compounds. I give you an example also like normal hexane. So the absorbance has to be on the lower energy side, above 190 nanometer, then we can see. So any molecule having unsaturated bonds or free non-bonding electrons that can absorb radiation of relatively low energy are called chromophores. Okay. Examples include alkenes. There is an unsaturation. Alkenes, alkynes, ketones, aldehydes, phenyl compounds, or different types of aromatic compounds. They all can absorb UV radiation. That is why UV has become so popular for the analysis of different types of samples, different types of compounds. A chromophore refers to a functional group that absorbs light, such as it can be a carbon-carbon double bond, carbon-oxygen double bond, nitrogen-nitrogen double bond, like nitrogen-oxygen double bond, like that. Okay. And it exhibits a characteristic absorption spectrum in the ultraviolet or visible region. Okay. Now, there is a possibility that one compound may contain more than one chromophore. At least one chromophore should be there. Then only the compound can absorb UV radiation. Otherwise, it cannot. But there are many compounds where the compound contains more than one chromophore. It can be 2, it can be 3, it can be 4, like that. Then we call these type of compounds are multi-chromophoric systems or multi-chromophoric molecules. A molecule may contain 2 chromophores, 3 chromophores, like that. So those type of compounds are also there. Then you will also come across another term like oxochrome. What's an oxochrome? That is also a functional group. Oxochrome is also a functional group, but this functional group will not absorb UV by its own, but it can influence the absorbance of a chromophore. It's something like a catalyst. It will not absorb by itself. If the compound contains only an oxochrome, it will not absorb UV radiation. But if there is a chromophore in the molecule, and if there is also an oxochrome, this oxochrome can always influence the absorbance because of the chromophore. And what way it is going to influence? The absorbance, intensity of absorption because of the chromophore can be maximized. There will be an increase in the degree of absorbance, intensity of absorbance because of the chromophore due to an oxochrome. That means the oxochrome can increase the intensity of absorption because of the chromophore. Number one. And there is one more. It can also shift the wavelength of maximum absorbance to longer wavelength. That means there is a chromophore. For example, there is a chromophore in the molecule. And because of this chromophore, the sample is absorbing at say 245 nanometer. I am giving a random figure. The compound is absorbing the maximum absorbance. That is what normally we call lambda max value, is at 245 nanometer. Now, if an oxochrome is present in the molecule, probably this lambda max will get shifted to longer wavelength. Instead of 245, it may go to 270 or 280. That means it is getting shifted to longer wavelength. That is the second effect. So an oxochrome has the effect of shifting the chromophore peaks to longer wavelengths as well as increasing their intensities. Initially, the intensity absorbance was only 0.6 because of a chromophore. Now, if there's an oxochrome present, the intensity may increase, for example, from 0.6 to 0.7 or 0.8. So increase in intensity of absorption and shifting of the lambda max to longer wavelengths. These are the two effects an oxochrome will induce in a molecule in presence of a chromophore. And examples of oxochromes, you can say hydroxyl groups, OH groups, or amino groups, NH2, thiol groups, SH groups, halogens, they all can act as oxochromes in a molecule. Okay. Now a compound also, I told you, can have more than one chromophore. And when the number of chromophores is increasing in the molecule, lambda max value will go to longer and longer and longer wavelengths. An example, I have taken out an olefin. Olefin is a single but double bond. That's a double bond. One double bond is there. And it has got a lambda max value somewhere around 190 nanometer. Okay. Now, if you consider a diolefin, a conjugated diolefin which contains two double bonds, and the lambda max will go to 270 nanometer. From 190, it has gone to 270 nanometer. Now, if I consider a triolefin, conjugated triolefin which contains three double bonds, my lambda max is getting again shifted to 250 nanometer. Because a double bond is a chromophore. A double bond is a chromophore. That way, benzene is a conjugated system. It has got three double bonds. That means it contains three chromophores. So you consider one benzene ring as a chromophore, and it is a conjugated system. That is why any sample which contains a benzene ring will have maximum absorbance in UV somewhere around 254 nanometer. Some plus minus slight this thing is there, but it will be somewhere around 254 nanometer. It will have a very, very strong absorption UV. Solvent cutoff values. This is very important while you are preparing a solution. In UV, most of students, if you are analyzing samples, you have to prepare a very dilute solution, and then you have to measure the absorbance in the UV spectrophotometer. You have to make a very, very dilute solution. If you prepare a very concentrated solution, your absorbance will be too high. and it will go to non-linear part of the detector and your readings will not be correct. So you have to dilute the sample by dissolving in a suitable solvent. You have to control the concentration so that the thumb rule is your absorbance value should lie between 0.3 to 0.8. You have to adjust the concentration of your sample in such a way that your absorbance value lies between 0.3 to 0.8. If it is more than 0.8, that means your concentration is more. You have to dilute the sample further. And if your absorbance is much less than 0.3, that means your sample concentration is too low. You have to add a little more sample. So to adjust it, the absorbance value should lie between 0.3 and 0.8. Okay. For that, you are going to dissolve the sample in a suitable solvent. There are a lot of solvents available in your lab. And while selecting the solvent, you have to consider something called solvent cutoff value. And what is, to make you understand, I will take an example of chloroform. Chloroform is a very powerful solvent. So many different samples can freely dissolve in chloroform. It's a very popular solvent. It has got a cutoff value 240 nanometer. What does it mean? 240 cutoff value for chloroform. What does it mean? Now you take an example of a pharmaceutical compound. The drug is totally soluble in chloroform. Okay. Now this particular drug has got a lambda max at 225 nanometer. Again, a random figure, 225 nanometer. Sample is really soluble in chloroform. And I dissolve the sample in chloroform, made a solution, and I'm going to I'm going to read the absorbance value. I will get certain absorbance value, but this absorbance value will be excessively high because now we have to look at the solvent cutoff value. Solvent cutoff value for chloroform is 240 nanometer. Lambda max for your sample is 225 nanometer. And what is cutoff value? Cutoff value means 240 nanometer. The cutoff means below 240 nanometer, your solvent, that is chloroform, is going to absorb heavily. And above 240 nanometer, the absorbance because of chloroform is going to reduce drastically. That means above 240 nanometer, the absorbance will decrease, and below 240 nanometer, the absorbance will increase. So now look at the lambda max of your sample, 225 nanometer. So if you measure this solution, which is made in chloroform, and you make the measurement 225 nanometer, that absorbance value will be very, very high because your chloroform is also contributing. Chloroform is also absorbing at 225 nanometer because it is much below 240 nanometer. So that means for this particular measurement, chloroform is not a suitable solvent. Now, the second argument, same drug. Now you assume the drug has got a lambda max at 295 or 300 nanometer. In that case, can you use chloroform? Absolutely yes, no problem, because 300 nanometer is much above 240 nanometer. So 300 nanometer, the absorbance because of chloroform will be practically very, very minimum. So you can use chloroform at 300 nanometer because much above 240 nanometer. So that is the meaning of solvent cutoff value. And different solvents have got different cutoff values. Some of the best solvents we can think of, acetonitrile, has 190 nanometer. That means it is practically the entire UV range acetonitrile is transparent. Similarly, HPLC grade water, very good quality HPLC grade water, again 190 nanometer is totally transparent sample. You can use cyclohexane 195 nanometer, isooctane 195 nanometer, methanol 205 nanometer, normal hexane 201 nanometer. So different solvents have got different cutoff values. So before selecting the solvent for making the solution, you also should consider what is the solvent cutoff value for the solvent. Otherwise, you will be getting a absorbance value which may not be correct. Okay. So now you look at this dye sample. This is a water-soluble dye. And looking at the structure of this compound, you will be able to say whether it is going to absorb in the UV visible spectrophotometer or not. You can count the total number of benzene rings present in this molecule. There are total 6 benzene rings are available. Each benzene ring is a chromophore for us. So that means this particular molecule contains 6 different chromophores. So that means it is going to absorb highly and it will absorb in the visible region. That means because of multi-chromophores, the absorbance will go to longer and longer wavelengths. It will enter the visible region and you can do a colorimetric analysis for this compound. Now, tryptophan is an amino acid. Looking at the structure, can you imagine whether it will absorb or it will not absorb? It contains a benzene ring itself, makes it a UV absorbing compound. Okay. Similarly, another vitamin A. Vitamin A is a oil soluble vitamin, normally analyzed by HPLC using a UV spectrophotometer detector, because you can look at the structure of vitamin A, it's a conjugated system. And because of the conjugation, the compound is highly UV absorbing and it can be easily detected and measured using a UV spectrophotometer detector. Normally, we analyze vitamin A by HPLC with a UV detector. Okay. Now, look at anthracene. Anthracene is a polyaromatic hydrocarbon. 3 benzene rings are fused together. Again, it becomes a is a multi-chromophoric system. And if you look at the lambda max, see, it has already crossed 350. Because of the presence of multiple chromophores, the lambda max has already gone beyond 350. That means it is going to longer and longer wavelengths. So that's the effect of your multi-chromophores present in the molecule. Now, effect of substitution. There are 4 different effects you should understand, the students. There is one is hyperchromic effect, one is hypochromic effect. Third one is called beta-chromic effect, which is called red shift. And the last one is called hypsochromic effect, which is called a blue shift. So, to make you understand, I have just recorded the spectrum of a compound over UV and visible range, and it has got a maximum absorbance, lambda max, somewhere around 400 nanometer. 400 nanometer is the lambda max, and around 0.6 is the absorbance value. 0.6 or 0.7, roughly 0.6 to 0.7 is absorbance value. Okay. Now, if you are adding a certain substituent on the molecular structure, this structure can increase the absorbance value from the intensity of absorbance can be increased by the addition of the substituent. That means the intensity will increase from 0.7 to 0.8 or 0.9. At the same time, the lambda max will not change. Lambda max will remain at 400 only. That is one possibility. That's called a hyperchromic effect. Hyperchromic effect is an addition of a substituent will increase the intensity of absorption without changing the lambda max. Now the opposite also can take place. Another substituent is going to reduce the intensity. From 0.7 it come to 0.5 or 0.6. But again, your lambda max is not changing. So that is called a hypochromic effect. So hypochromic effect and hyperchromic effect. There is no change in the lambda max. There is no change in the lambda max value. What is changing is the intensity of absorption. In hyperchromic, it is increasing, and hyperchromic, it is decreasing. Now the other two, one is called beta-chromic, and the last one is called hypsochromic. And what is beta-chromic? Beta-chromic is a different substituent on the molecule will shift the lambda max value, but it will not change the intensity of absorption. 0.7 means it will remain 0.7 only, but lambda max will change, say, from 400 nanometer to 500 nanometer or 600 nanometer. Is going to longer wavelengths. Any shift towards the longer wavelength is always called a red shift. So that is why it's called a beta-chromic shift, or it is called a red shift. Again, the opposite can happen. A different substituent can shift the lambda max to lower wave number side. That means higher energy side. So from 400, it can come to 300, or it can come to 350 or 250. But your intensity of absorption will remain same. So that is called hypsochromic shift. And any shift towards shorter wavelength is always called blue shift. That is, shorter wavelength means you're going for higher energy side. Longer wavelength means you're going to lower energy side. So lower energy side shift is called a red shift, and shift towards higher energy side is called a blue shift. So these 4 different types of effects can take place: hyperchromic, hypochromic, betachromic, and hypsochromic. Sometimes when you're adding changing the solvent for dissolving the sample, suppose you have a drug sample, you dissolve in solvent number 1, you get a certain lambda max. Sometimes if you use a different solvent, many times it is observed that your lambda max can be slightly different. That is basically because of these effects. Intensity also can sometimes change. So these are the effects of substituents or sometimes even dissolving solvents. Calibration and BS law, and all of you should understand UV is a 100% quantitative analytical technique. It is not today, nobody is using UV as a qualitative identification technique. It is a 100% quantitative technique. Why we cannot use it as a qualitative technique, you will understand going forward. But everyone today in industry also, people are using UV for excellent quantitative analysis. Okay. Now, what is to be done? The sample is to be dissolved in a suitable solvent. As I told you before, it has to be a very dilute solution. You have to control the concentration of the sample. And then you have to take the sample solution in a cell, sample cell. It is always called a cuvette. Cuvette can be made of glass, it can be made of quartz, and it can also be made of plastic. All 3 types of cuvettes are available. Plastic cuvettes are available, glass cuvettes are available, quartz cuvettes are available. So please keep in mind, if you are making the measurement in the UV region, you have to use always a quartz cuvette. You cannot use a glass cuvette, because glass will absorb UV radiation. And if you use a glass cuvette in the sample compartment, your absorbance value will continuously fluctuate. It will never remain steady. These type of complaints we get from industry also. And when our service person or when an application person goes there, we find the customer is using a wrong cuvette. And that's then normally the tendency of the people is to blame the equipment. There is a problem with your equipment. I am not getting a steady absorbance value. It is continuously fluctuating. They will try to blame the equipment, but it is not the equipment that is responsible for this. It is the user who is responsible for this because he has used a wrong cuvette. So if you use a glass cuvette, you will never get a steady reading. It will continuously fluctuate. So you have to please keep in mind, any reading in the UV region, you have to use a quartz cuvette only. But if you are working in the visible region, you can use anything. You can use a glass cuvette or a quartz cuvette. There is no problem. Okay. Now, what is the solution is taken in the cuvette, and please don't fill the cuvette full. If you fill it completely to the brim, it will start overflowing. All those problems will be there. So you can fill the cuvette maximum up to around 75% of the total volume. The cuvette is approximately 2.8 ml to 3 ml. That's a total volume of a standard cuvette. And this standard cuvette is 1 centimeter by 1 centimeter. It's a square cell. 10 mm by 10 mm, or you call it as a 1 centimeter by 1 centimeter. It's a square cell. All the 4 sides are 1 centimeter. And it has got an approximate volume of around 3 ml or something. And you need to fill it up to around 75% of the total capacity, because your light is going to pass through almost through the 50% of the length. So 75% if you fill, that is more than sufficient. Don't fill it full so that it will not overflow. And then you keep this sample compartment. Light from the light source will be passing through the sample compartment, which contains the solution. And depending upon the type of solution, depending upon the concentration, some amount of energy will be absorbed. So the I0 is the intensity of the incident light. It will be passing through the sample compartment. And then what is coming out is called the transmitted light. Transmitted light intensity is I1. I1 will be always less than I0. I0 is always 100%. I1 will be less than 100%. How much? Depends on the sample concentration. How much the sample is going to absorb. Accordingly, the energy will decrease. The intensity will decrease. So intensity of I1 will be always less than intensity of I0. I0 is the incident light, I1 is the transmitted light. So if I take the ratio I1 by I0, that is called the transmittance value. That's called the transmittance value. Suppose I0 is always 100. Suppose I1 is 90. 90 divided by 100, 0.9 is the transmittance value. And if I multiply this transmittance I1 by I0 multiplied by 100, that will give me percentage transmittance. That means 90 by 100 into 100. So 90% transmittance. That is called the percentage transmittance, 100%, 90% transmittance. Okay. Now, when you are going to do quantitative analysis by UV, you should know what are the laws. There are certain laws to be observed. The laws of spectrophotometry. There are two very important basic laws, and the third one, which is a combination of the two.
Hello.
What is law number one? Lambert's law. What is Lambert's law? Absorbance of your sample is directly proportional to the path length of the medium. Path length means what? I hope all the students understand what is the path length. Path length is the distance through which the light is traveling. So if I'm using a 1 centimeter by 1 centimeter square cell, the distance is 1 centimeter. The distance, the light passing through 1 centimeter of the sample, that is the path length. And I have different path length cells. Right from 1 centimeter to 10 centimeter, different path length cells are available. But standard is always 1 centimeter. So path length is 1 centimeter. If I increase the path length, my absorbance also will increase. So that is Lambert's law. Absorbance is directly proportional to the path length. That is the path length of absorption. Then second law is called Beer's law. What is Beer's law stating? Absorbance of your sample is directly proportional to the concentration of the sample. I told you if you increase the concentration, your absorbance value will increase. So absorbance is directly proportional to concentration. That is Beer's law. Now we can combine these two together. Lambert's law plus Beer's law, we get Beer-Lambert's law. And Beer-Lambert's law says absorbance is directly proportional to the concentration and the path length. And that is what is Beer-Lambert's law. Okay. So this is Beer-Lambert's law. Absorbance, capital A is the absorbance, what you are getting from the equipment. The moment you keep your sample inside the sample compartment, you get an absorbance value on the screen. That is your A value. Capital A is the absorbance reading. Is equal to, there are three terms. One is epsilon, which is a constant. Epsilon is nothing molar absorption coefficient of the sample at a certain wavelength. Molar absorption coefficient. That's a constant. For a given sample at a certain wavelength, it is always a constant. Then epsilon multiplied by L. L is nothing but the path length. Now, if you are using a standard cuvette, path length is always 1 centimeter. So that is also a constant. Multiplied by C. C is the concentration of the sample. And C is the only variable. Epsilon is a constant. L is a constant. C is a variable. So if I take out these two constants, epsilon and L, I can rewrite the equation as absorbance is directly proportional to concentration. That's all your Beer-Lambert's law says. And every spectrophotometric method which is used for a quantitative analysis has to obey Beer-Lambert, whether it is UV visible spectrophotometry, infrared spectrophotometry, or atomic absorption spectrophotometry. Your Beer-Lambert's law is to be obeyed, then only you'll get a correct quantitative analytical result. Okay, so otherwise, no. Okay. Now, limitations of Beer-Lambert's law. There are certain limitations also. All these limitations, the most important limitation is the concentration itself. So what are the limitations of the Beer-Lambert's law? One is increase in analyte concentration. I told you some time back, you have to make a very, very dilute solution. If you increase the concentration, your readings will go to non-linear part of the, every electronic detector has got an LDR. LDR means linear dynamic range. And beyond that, and if you are crossing that LDR limit, it will go to the non-linear part of the detection, and then those readings will be absolutely wrong. That means your quantitation will be incorrect. So you have to adjust. That is why we always advise the users, adjust the concentration in such a way that you get a reading between 0.3 to 0.8, so that you can be 100% sure the reading is lying in the linear part of the detector. That's the LDR region, linear dynamic range. So increase in analyte concentration, that's one of the most important thing you have to always keep. You have to adjust the concentration. Chemical deviation due to physico-chemical interactions. If there is an interaction between the sample and the solvent, those type of this, and there's some complex formation, then that also can affect your readings. Stray light. And what is stray light? I will tell you. I mean, in the coming slides, any stray light means any unwanted light that is coming to the detector is called a stray light. Fluorescence by the absorbing species. Suppose your sample has got a fluorescence tendency, that also can affect your readings. Changes in refractive index of light, non-parallel light beam, and these are all related to the hardware of the system. Instrumental limitation due to noise. Noise means any disturbance in the signals. That's called a noise, and these are all related to the hardware design of the equipment. Okay. Now, most important effect is concentration. Effect of analyte concentration. So Beer-Lambert's law is applicable to very, very dilute solution. That's why I was repeatedly telling you, you have to make a dilute solution, and the instrument is so powerful, the detector is so powerful that even after making a dilute solution, you will get a reasonably good absorbance value because the detectors are very, very powerful nowadays. So applicable to very dilute solution. And if your concentration is more than, it is a general rule, if the concentration solution is more than 0.01 molar, then you can expect some deviation from linearity. And if deviation is taking place from the linearity, then your results will be incorrect. So what is to be done? You have to dilute the sample to a lower concentration. Sometimes you may have to try out some 1, 2, 3 different dilutions. Which dilution is giving you the correct reading, that you have to try it out, trial and error. The high concentration, more molecules are packed in one volume, absorbance will increase, and Beer-Lambert's law will not be obeyed. Okay. Stray light, I mean, just for the students, I mean, I'm not going into details. Stray light means, in a layman's language, any unwanted light that is coming to the detector is called a stray light. So stray light is defined as detected light of any wavelength that lies outside the bandwidth of the selected wavelength. What does this mean? Suppose I am going to measure my sample in a UV visible spectrophotometer, and my lambda max I am going to set at 254 nanometer. That means I want to make the measurement at 254 nanometer. That means 254 nanometer light only should go to the detector. Suppose maybe because of the design of the equipment, other than 254 nanometer, some other wavelengths are also going there. 260 is also going there. 250 is also going there. But they are all unwanted wavelengths. And these unwanted wavelengths or unwanted light that is reaching the detector is called a stray light. And if the stray light is more, again, you will have problems in your readings. It will not be a correct reading. But but stray light is not in your hands. It is to be taken care of by the manufacturer of the equipment. Stray light is basically because of how the hardware system is designed. It depends on the design of the hardware system. So there is an equation used to calculate transmittance. The equation that is used to calculate transmittance can be written as T is equal to, T is the transmittance value, is equal to I plus IS divided by I0 plus IS, where T is the transmittance value, I0 is the intensity of the incident light, I is the intensity of the transmitted light, and IS is the intensity of the stray light. Okay. So there are different methods to find out what is the stray light. If you students happen to see what is method 857, method 857 USP, and it gives lot of information regarding the validation of equipment. There, how the determination of stray light is well defined and described in detail. I mean, that itself is a big topic to be discussed. I'm not going. So method 857 in USP, if you want, you can refer that. Okay, so how the stray lights are to be determined. At 3 different wavelengths, we have to determine the stray light using 3 different types of standards. And all these are described in method 857 in USP. Now, if stray light is more, lot of deviation will take place. Ideally, your stray light should be 0.00. That is the ideal condition. But it is not possible for any manufacturer to design an equipment with zero sterility. Some sterility will be there. 0% sterility is not possible. But they will try to reduce the sterility to the minimum possible level. So today we have equipments where the sterility is only 0.00001%. To that level we can go. But we cannot say sterility is exactly 0%. That is not possible. So sterility increases, you can see from the graph, linearity is going to be deviant. I mean, there is going to be a lot of deviation from the linearity. See, if the 1% sterility, that's the blue color, the last one, you see 1% sterility, lot of deviation, 0.1%, 0.01% is the red color. So even if it is 0.01% sterility, there is a deviation from linearity. You can see the red color slightly deviating. And that green color, 0.1%. And blue color, 1%. Tremendous deviation. So today, manufacturers are trying to, the instrument manufacturers are trying to reduce the extent of the degree of sterility to the bare minimum possible level. So we have got an equipment which gives a sterility of 0.00001% or something like that. But instrument will be expensive. So those type of equipments are used basically for high-end research activities, not for routine instrument, not for routine analysis. Okay. Now, UV spectroscopy in pharmaceutical analysis. Applications in a lot of applications in pharmaceutical analysis. It's a robust workhorse method, UV. It's a very, very robust method for quantification of drugs in formulations and determination of PK values of some drugs. Used to determine release of drugs from formulations at time. That is dissolution testing. All of you must be knowing about dissolution testing, content uniformity testing, cleaning validation in API manufacturing. UV has got tremendous amount of applications. Okay. Now, it has got certain limitations also. So when it comes to the limitations of UV, moderately selective. It's very, very moderately selective. Moderately selective means what? That is the reason why today we are not using UV for qualitative analysis. I will give you two different compounds A and B. Entirely different compounds A and B. Two different chemical compounds. It can be drug compounds or can be whatever it is. If you record the spectrum of A and record the spectrum of B in a UV spectrophotometer, and if you compare these two spectra, your observation is that these two spectra are more or less identical. You will not find many differences in these two spectra. They are almost identical. That means you will not be able to differentiate compound A from compound B. It is very difficult for us to identify or differentiate one compound from another compound by looking at the UV spectrum. That's a major limitation. Only moderately selective. And the compound has to contain a chromophore, otherwise the compound will not absorb UV. It becomes a UV transparent sample and not readily applicable to analysis of different mixtures. It's a very complex mixture, then UV analysis will be difficult. Now, for example, UV spectra, I am giving you two steroids. One is hydrocortisone, second one is beta-methasone. Okay, and if you record the spectrum of hydrocortisone and beta-methasone, say between 200 nanometer to say 300 nanometer, and you can look at the UV spectra of both the compounds, they are more or less identical. Even the lambda max are coming very, very close to each other. And the UV spectrum of hydrocortisone and UV spectrum of beta-methasone are very, very similar. You will not be able to differentiate. On the contrary, if you take these two steroids and record IR spectrum, these two IR spectra will be different. That is why today IR is scoring as a excellent qualitative identification technique, whereas UV has become an excellent quantitation technique. Okay, it is not a popular qualitative analytical technique because of this. Okay. Now, if you look at some of the corticosteroids, lambda max value, hydrocortisone, 240 nanometer, lambda max. Beta-methasone, again same, 240 nanometer. Clobetasol butyrate, 236 nanometer. Beta-methasone sodium phosphate, 241 nanometer. exactly same lambda max. So that means you'll not be able to differentiate even by looking at the lambda mass values, and they're all very, very similar. The molecular weights are different, but the lambda max values are very similar, and they all will produce very, very similar UV spectra. That means differentiation, say, between hydrocortisone and betamethasone or hydrocortisone and clobetasol butyrate, it will be difficult from UV spectrum, but they can be differentiated by IR spectrum. Okay, now even under acidic conditions and basic conditions, the spectra can be slightly different. This is a UV spectrum of procaine under acidic and basic conditions. You can see the spectrum recorded where the solution is prepared in 0.1 molar sodium hydroxide solution, and another one is 0.1 molar hydrochloric acid. The lambda, the absorbance values are drastically different, but the lambda max values are more or less same. Only the change is coming in the intensity of absorption, and the lambda max is coming fairly close to each other. Similarly, phenylephrine under acidic and basic conditions, one is in 0.1 molar sodium hydroxide, one is again 0.1 molar hydrochloric acid. Lambda max is either not exactly same, but they are coming very, very close to each other, and the peak shapes are also, the band shapes are also very close to each other. So penicillin by derivatization. Penicillin, see, British Pharmacopoeia utilizes the formation of a derivative in order to quantify penicillin in a formulation. See, some of the penicillins do not have a very distinctive chromophore. So since there is no distinctive chromophore, they will not absorb UV radiation. That means they cannot be analyzed by UV. But now, if you convert this penicillin into a complex by react with the derivatizing agent, nothing but a derivatization reaction, the complex can absorb UV, and thereby you can quantify the penicillins. So using the formation of a complex with mercuric ion in presence of imidazole as a catalyst, a derivative of penicillin is produced, which has an absorption maximum, that is lambda max, somewhere around between 325 nanometer and 345 nanometer. So this assay method is used by BP for the analysis of preparations containing ampicillin, amoxicillin, cloxacillin, flucloxacillin, etc. And this is the derivative reaction. Protein melting temperature. These are basically biotechnology applications. Protein melting. Absorbance spectra of proteins result largely from the presence of aromatic amino acids. All these proteins contain tryptophan, tyrosine, phenylalanine. And because of the presence of these amino acids, aromatic amino acids, they have got UV absorbance properties. A protein at a normal temperature, room temperature, has got a very, very specific tertiary structure. And this specific tertiary structure creates an electronic environment for the aromatic amino acids. Okay, and so they have got a certain UV absorbance characteristic also. Now, if you heat this protein solution at a certain temperature, what will happen? This structure will get lost. And that means the protein starts melting. And during the course of melting, the specific structure of the protein will be lost. And when the specific structure is lost, there will be changes in the electronic environment around the aromatic amino acids. And these changes will result in spectral absorbance changes also. Okay. So thereby we can use a UV for protein analysis also. We have equipment for that. We have got software for that. Nucleic acid melting temperature. Deoxyribonucleic acid DNA in normal state comprises of two strands of deoxyribose molecules helically wound around the same axis. So it has got a helical structure. And these two strands, or what you consider as two strings or two strands, they're all connected by hydrogen bonds. And these hydrogen bonds are between purine and pyrimidine bases. Adenine is joined to thymine, so there is a AT pair, and guanine is connected to cytosine. There's a GC pair. So there are two types of hydrogen bonds present in the nucleic acid. One is an AT pair, and one is a GC pair. Adenine, thymine pair, and guanine, cytosine pair. Okay, now these bases are primarily responsible for UV absorbance, and DNA measurements are always done at a max of 260 nanometer lambda max value. So we have DNA RNA quantification method we do by UV, and we make the absorbance, we measure the absorbance values at 260 nanometer. So as in a multi-component system, so your DNA contains 4 different types of compounds. Adenine is there, guanine is there, cytosine is there, thymine is there. So the absorbance of the DNA molecule, the total absorbance of the DNA molecule is the sum total of all the absorbances because of all these 4 different compounds. That is absorbance of adenine plus absorbance of guanine plus absorbance of cytosine plus absorbance of thymine. Okay, now if a molecule is heated, now DNA molecule, the solution is heated, the hydrogen bonds will break. Okay, when you are heating, these bonds are going to rupture. And when the bonds are rupturing, the helical structure is going to unwind. And when it is unwinding, the absorbance is going to increase. Okay. And this process is known as the denaturation process, known as melting of DNA. And what we do normally, we prepare a solution of the nucleic acid, and then when in the sample compartment, what we do, we measure the absorbance at 260 nanometer. At the wavelength is fixed. Lambda max is always fixed at 260 nanometer, and we measure the absorbance at different temperatures. So in the DNA melt experiment, what we do, the temperature of DNA solution is increased gradually in a stepwise fashion, and the absorbance at 260 nanometer at each temperature is measured. So we increase the temperature, and at each temperature, the absorbance is measured, but your lambda max is fixed. And then we plot a graph, temperature versus absorbance value. And the middle portion of this graph, the midpoint of this graph is the TM value. It's called the melting temperature of the nucleic acid. And the melting temperature gives a lot of information to the biotechnologists because different types of structures can have different melting temperatures. Okay, now this melting temperature, that is called the TM value of a particular DNA system, also depends primarily on the percentage of GC pairs in the sample. Okay, that is each of which contain 3 hydrogens. Guanine cytosine pair will contain 3 hydrogen bonds, whereas adenine thymine will contain only 2 hydrogen bonds. If your GC percentage is more, the higher the observed melting temperature. So the melting temperature gives a lot of information. So that is a very, very important analysis, and especially in biotechnology field. So we have system for that. We have got separate inbuilt software also can take care of this type of analysis. Then similarly, enzymes. Direct UV analysis of a component in a very complex biological sample is difficult because of interferences. Biological samples contain a lot of interfering matrices. So an individual compound, sometimes it's very difficult to make the measurement of an individual component. Otherwise, you'll have to separate it by chromatography technique, but it's time consuming, it's laborious. But then you can use an enzyme method for that. Enzyme assays can be used in the indirect analysis of one compound or a group of compound in a very, very difficult matrix. Any change in the sample following the addition of an enzyme will result only from the reaction of the specific compound. The enzyme will react only with the specific compound, and then there can be changes in the absorbance pattern, and that can be studied. So this, and we also have a enzyme kinetic factor available in the software as a routine, and it's a by default that feature is available in the software. So we can do a lot of studies using this. Multi-component analysis. Multi-component analysis means spectrophotometric method of pharmaceutical drugs often involves the measurement of absorbance of samples containing one or more absorbing compounds. The sample may contain different compounds, and all these different compounds may be absorbing. Okay, then it becomes a very difficult task for the pharmaceutical analyst. And he encountered the situation wherein the concentration of one or more components is required in a sample which may contain other absorbing compounds that can interfere with the determination. And this is basically called multi-component analysis. Okay. So the basis for multi-component analysis is based on two assumptions. Number one, at a given wavelength, the absorbance of a sample solution is the sum of the absorbances of all the compounds plus the sample. Number one, that is the total absorbance is the sum total of absorbance because of different compounds of the system. Second assumption, the excipients present in the formulation are not absorbing at the selected wavelength. So these two conditions, these are the two basics of multi-component analysis. It can be this can be applied in a formulation. Derivative UV visible spectrophotometer. I am not going into too much of details. Derivative spectroscopy uses first or higher derivatives of absorbance with respect to wavelength for qualitative analysis and for quantification. When you are recording the spectrum of a sample in a UV visible spectrophotometer, the spectrum what you are getting is called the zero order spectrum. And this zero order spectrum can be converted to different higher order derivatives, first order, second order, like that. And these are all mathematical calculations. And what is the importance of derivatization? The concept of derivatizing, it's a very long concept of derivatizing spectral data was introduced in 1950s, but then nobody gave much attention to that. And but the actual what you call introduction of microcomputer in the late 1970s made it generally practicable, and a lot of developments have come and which try to make use of derivatization in UV spectrophotometry in late 1970s. And this significantly increased the use of derivative technique. So in derivative spectroscopy, what we do, derivative spectroscopy is an advanced spectroscopy technique based on the derivative spectra which are generated from the zero order ones. As I told you, what you get when you keep the sample is a zero order spectrum, and from the zero order spectrum we can generate higher derivatives of the spectrum. And the derivatization of zero order spectrum can lead to separation of overlap bands. A major advantage, suppose your compound has a major compound, it may be
हेलो गिरिराज सर। हेलो गिरिराज सर। सर अनम्यूट है शायद आपका।
Yes, sir. I am connecting again. There was a problem, so I am connecting again, sir.
ओके सर। स्टूडेंट आप लास्ट में क्वेश्चन आंसर कर सकते हैं ना सर से, गिरिराज सर से, जो भी आपके डाउट्स हैं जो भी हैं सर क्लियर करेंगे। आप लास्ट में क्वेश्चन आंसर कर सकते हैं। श्योर सर?
Hello. Hello.
Yes, sir.
Can you hear me now?
Yes, sir.
Okay, okay. Sir, can you see the slide now?
Yes sir.
Okay. There was some problem in between. There was a connection problem. So I again relogged it. Okay. So this derivative spectroscopy allows the quantitation of one or more targets without any initial separation. So even if two compounds are overlapping, you can separate it by a suitable derivative spectroscopy technique, and then you can separately quantify them. So in derivative spectroscopy, what we are doing is we are plotting delta A by delta lambda, that is rate of change of absorbance with respect to wavelength against the wavelength. So delta A by delta lambda is plotted against wavelength lambda. And the derivative spectrum contains sharper peaks where better location of peaks and wavelengths maxima can be achieved. So even if there is an overlapping band you are getting, by adopting a suitable derivative technique, you can separate it. You will be getting sharper peaks and you can separately identify and quantify these two compounds. So not only first derivative of the absorbance spectrum can be obtained, you can go to 4 derivatives. That is first derivative, second derivative, third derivative, and fourth derivatives. But please keep in mind, when you increase the order of derivatization, when you are going from first order to second order, from second order to third order like that, the noise level also will increase. So when the noise level increases, there is a chance that your sensitivity can be slightly compromised. So if you are happy with your zero order spectrum, and if you are okay with the zero order spectrum, there is no point in going for a derivatization. Okay, so this can be applied in very difficult conditions, but many people, I have not seen many people using a derivative technique many times. Okay, number of bands, when you go for derivatization, the total number of bands you are going to observe will be equal to the derivative order plus 1. That means if you are going for first derivative, you will find two different bands. Because 1 plus 1. If you are going second order derivative, you will find 3 different bands, 2 plus 1. If you go for a third derivative, you will find 4 different bands, 3 plus 1 like that. And in fourth derivative, you will find total number of 5 different bands because 4 plus 1. That is the order of derivative plus 1 will be the total number of bands that you will be able to see. Now, for example, derivative spectroscopy is excellent technique for the determination of multi-components in a sample, if they can be resolved. So I can use, even if the compound gives me an overlapping spectrum, I can use a derivative technique and I can specifically see here it is the X and Y, 2 different compounds are there. My zero order spectrum gave me an overlapping peak. By using a first order derivative, I could easily separate my 2 different compounds X and Y, and I could separately quantify X and Y. So that's a advantage of going for a derivative technique. Okay. Now, students also should understand something about the basic components of a UV visible spectrophotometer. Very simple diagram. There is a light source, there's a monochromator, there's sample compartment, detector, and finally a recording output. Okay. Now, what is the, this is the same thing what we have seen. I have written here: sources, light source, wavelength selector, monochromator or filter, sample compartment, detector, and readout device. Readout device is nothing but your PC and printer. That's all. And either your equipment can be single beam equipment or a double beam equipment. Okay. Now, can anybody tell any student? The question is only for the students. What is the source of light in UV and visible? In a UV visible spectrophotometer, what is the source of light? Many of the students must be using this in your lab. I know, I am 100% sure. So tell me, what is the light source in UV? What is the light source in visible? Can anyone tell?
स्टूडेंट आप अनम्यूट करके क्वेश्चन का आंसर कर सकते हैं.
If you are using a UV visible spectrophotometer for some of your samples in your laboratory, you should know what is the UV source light and what is the visible light source. What is the UV source and what is the visible? That's my very simple question. Anybody? I am sure M.Pharm students, even B.Pharm students must be using a UV in your lab.
Hydrogen discharge lamp, xenon discharge lamp.
What is xenon? Xenon discharge lamp we don't use. Who is that? Are you a B.Pharm student or M.Pharm student? Are you a B.Pharm or M.Pharm student?
B.Pharm.
B.Pharm student. Are you using a UV visible spectrophotometer?
No, sir.
No. See, in visible region, we are using tungsten halogen lamp. Tungsten halogen lamp we are using in visible region. And in UV region, we are using deuterium lamp, D2 lamp. So D2 deuterium lamp is used in UV region and tungsten halogen lamp is used in visible region. So there are two lamps inside. In any UV spectrophotometer, UV visible spectrophotometer, there are two lamps, one for UV region, one for visible. Tungsten halogen for visible and deuterium for the UV region. Okay. And so that's the source of light. Then wavelength. So whatever is coming from the source, is coming to the monochromator. What is the monochromator? Anybody knows what is the use of monochromator? Any student? Why a monochromator is required in UV visible spectrophotometer? Or I'll put the question a different way. What is the function? What is the responsibility of a monochromator? What is the responsibility of the monochromator in a UV visible spectrophotometer? Anybody can answer?
Narrow the band wavelength, sir.
Narrow the band, yes, to a certain extent, I can consider it, but it has to be a little more precise. The answer has to be a little more precise. What you are telling is, partially I can agree, but it has to be a little more precise. Monochromator, any student? Anyone?
To isolate radiation of different wavelength.
Isolate what?
Isolate radiations of different wavelength.
Isolate means, are you referring to separate different wavelengths? If that's the case, your answer can be partially right. Okay, I'll tell you, monochromator.
It converts polychromatic light into monochromatic light.
That is the correct answer.
And produce single color, sir.
That is the correct answer. Conversion of polychromatic light into monochromatic light. That's the right answer. Because whatever light is coming from your source is a polychromatic light. Polychromatic light means light having many different wavelengths. That's called polychromatic. But then I don't want all these wavelengths to pass through my sample. I want only a single wavelength. So the monochromator is converting a polychromatic light into monochromatic light. Monochromatic light means light of single wavelength. Polychromatic light means light of multiple wavelengths. So when the polychromatic light is passing to the monochromator, whatever is coming out is a monochromatic light. Monochromatic light is a single wavelength. And how that is separated, you will see. And this monochromatic light will be passing through the sample compartment, and sample will absorb depending upon the concentration, and the remaining light will come out. It goes to the detector, and detector is going to give a electrical signal that will be processed by your PC and software. Okay, so that is what is read. So there are sources, there are continuous source. In UV spectrophotometer, UV visual spectrophotometer, we are saying continuous source. There are two different sources of light. One is called continuous source, one is called a line source. In atomic absorption, we are using a line source, whereas in UV visible spectrophotometer, you are using a continuous source. Continuous source means it is emitting lights of multiple wavelengths. And in the case of, on the left-hand side, you are using a tungsten halogen lamp, which will take care of the visible region, and it can even go to NIR region. Right from 320 nanometer, it can even go to 2500 nanometer. Complete visible as well as NIR region, it can go, tungsten halogen lamp. Whereas in the UV region, we are using a D2 lamp, that is called a deuterium lamp. And normally it is from 190 nanometer to, even though I have written 200 to 400 nanometer, to be very precise, is from 190 nanometer to 360 nanometer. So that's a UV range. So UV range is slightly smaller as compared to visible range. Visible range is slightly wider, whereas UV range is much lower. So 390 to 160 nanometer. So, and now the wavelength select. Wavelength selector, once upon a time we are using filters, and filters were all outdated now. Now we are using a monochromator. As one student correctly said, the monochromator is converting a polychromatic light into a monochromatic light. Okay, so that is and how this is done. So what is the what type of monochromators we are using now? Once upon a time we are using prisms. Again, prisms have become outdated. Now we are using a grating. We are using a grating monochromator. Grating monochromator is called a diffraction grating. That's a monochromator we are using in all the systems nowadays. Grating is made now, for example, it's a glass plate over which a very thin and uniform aluminum coating is done in vacuum. And over this coating, we are going to draw lines. How many lines we are going to draw? In 1 millimeter distance, sometimes we draw 1,600 lines or 1,800 lines, 1,200 lines, or even 2,000 lines we can draw in just 1 millimeter distance. Is it possible to draw to 1,600 lines in 1 millimeter manner? It's not possible. So it is all drawn by laser beam. So laser cutting is done. So that means you are actually cutting, making small grooves, 1,600, 1,800 grooves packed in just 1 millimeter distance. More number of lines or more number of grooves in the grating, more will be the separation capability or power of the grating. Or you can say more will be the resolution capability of the grating. Okay, now this grating is used as a monochromator. Okay, how it is done? This grating is mounted on a motorized turntable. Is mounted on a motorized turntable. Okay, now polychromatic light is coming and falling on the grating, and the grating is on a rotatable turntable. Now, so for example, now for this measurement, I have selected a wavelength 612 nanometer. It's a visible wavelength. So when I'm feeding this value in my software 612 nanometer wavelength, automatically the monochromator will turn because it is a motorized turntable. It will turn at one particular angle. Only 612 nanometer wavelength light will come out of the opening. You can see a small opening. That is called the slit value. The opening. Only this particular wavelength will come out to the opening. All other wavelengths are totally blocked. And that is how we get the selected or wanted wavelength from the polychromatic light. Now, if we change this wavelength from 612 to say, suppose I make it 254, that motorized turntable will again rotate, and at one specific angle, only 254 nanometer light will come out. So that is how we convert a polychromatic light into a monochromatic light with the help of a diffraction grating. And diffraction grating is when there are different types of diffraction gratings also. We are not going into those details, but diffraction grating is by and large a very, very powerful monochromator system in a UV visible spectrophotometer. Now, similarly, this slit width is also very, very important. Narrower the width of the slit, better will be the resolution. If the slit is very wide, what will happen? More amount of light will pass through together and there will be overlapping. Proper resolution will not come. But if you try to reduce the opening, that is the slit, opening I am making very, very small, then my resolution will increase. On the left hand side, you can see fine and right from, there are 5 different graphs. I have shown 1, 2, 3, 4, and 5. And the first one is graph number 5 is 2 nanometer opening bandwidth. I am getting a very broad band without any resolution. And look at the last one, spectrum number 1, where the slit opening is just 0.1 nanometer. And you are getting a very clear resolution of 3 different bands in the spectrum. So that means what you understand is when you reduce the slit width, that one normally we call the monochromator bandwidth, we reduce it, your resolution will always increase. Resolution will always increase. And that is what we want. We want to totally resolve all the components so that we can clearly pinpoint what the lambda max of each one, and then we can individually quantify those. Okay. Now, since you are going to use a UV visible spectrophotometer as a quantitative estimation technique, please keep in mind your measurements should be always at the lambda max value. If you change the lambda max value, if you change the wavelength from lambda max to a different wavelength, your sensitivity will come down. So as an example, I have shown on the right hand side, I have prepared 5 different solutions having maximum concentration 10 to the power of -2 molar and the lowest concentration 10 to the power of -5 molar. And in between, there are 3 more solutions, 10 to the power of -2 molar, 10 to the power of -3 molar, 10 to the power of -4 molar, 5 into 10 to the power of -5 molar, and 10 to the power of -5. And all the 5 solutions, we measured the absorbance value at the lambda max value, and we got the absorbance. We could measure the absorbance of all the solutions. Even the smallest concentration solution, 10 to the power of -5 molar, and we could measure the absorbance value without any problem. But when I change the wavelength to a different wavelength, lambda 1, which is not a lambda max value, you can see the absorbance intensities have drastically come down. And another interesting observation is 10 to the power of -5 molar absorbance I am not able to read, because I cannot read the absorbance of 10 to the power of -5 molar because the concentration is low. I am not able to see the absorbance value for that particular solution. That's the importance of making the measurements at lambda max values. So see that as far as possible, unless there is a specific condition, which I'm going to show one slide, your measurement should be always at lambda max value. That will give a very, very sensitive absorbance rate. This is a drug sample. Okay, in this I am making a measurement at lambda max value. I am getting a very good sensitivity for my drug. But unfortunately, my formulation contains another compound, which is an interfering compound, which is also absorbing at the same lambda max value. So that's a problem for us. That means this lambda max measurements cannot be done because of the interfering compound. Under those very, very rare circumstances, you can change or you can choose a different wavelength. Here I am used a lambda m. It's a different wavelength. Here also my drug is absorbing, but intensity has come down. But still it is okay with us because the interfering compound is not absorbing at this particular wavelength. So under those circumstances, you can think of changing the value, lambda wavelength value from lambda max to a different wavelength. Otherwise, you always should stick to lambda max value for all the measurements. Coming to some of the important applications of UV visible spectrophotometer. Why we use UV visible spectroscopy? For every sample, we can get a spectrum, easy sample concentration calculation, and affordable instrumentation. And some of the major limitations, little structural information I've already told you, very, very similar spectra for different compounds. So that is a problem we are facing, a major limitation for you. A lot of agricultural applications in food industry, color and consistency are very two important parameters as far as the user is concerned, the consumer is concerned. Color of the product is very important. Consistency of the food product is very, very important. All these can be measured, can be analyzed and evaluated by UV using a UV visible spectrophotometer. And we are adding different types of small amounts of chemicals in the food product formulation, like antioxidants, and all these are preservatives, antioxidants, anticoagulants, anti-settling agents, and all these can be very precisely quantified by a UV. Even color of a food product can be measured. We have got a separate color measurement system, which can be used along with a UV visible spectrophotometer, and the color of the product can be evaluated. Similarly, in beverage, liquor manufacturing, software manufacturing, UV has got a lot of applications. Again, addition of preservatives, color of the product, these are all very, very important. Academic applications, leaf analysis, chlorophyll content. Depending upon the chlorophyll content, the greenness of the leaves can be different. So you can actually quantify different chlorophylls in the leaf. These are basically botanical research laboratories. They do this type of analysis. Biological applications, I've already told you about protein analysis and DNA, nucleic acid analysis, and kinetics. They monitor rate of reaction and enzymatic reaction. And we have seen some examples also. And the industrial applications, pharmaceutical manufacturing, UV was a absolute must in every pharmaceutical industry or a pharmacy college, because we have got tremendous number of applications for UV. In industry, right from raw material analysis, dissolution testing, continuum uniformity testing, intermediate analysis, cleaning validation, many applications are than pharmaceutical. Similarly, in chemical industry also, quality control, raw material testing. So UV has become a well-accepted technique in many different industries. Academic and government applications, environmental testing, especially contaminants in streams and water, research, purely research applications in universities and CSIR laboratories like optical materials. In optical materials, people are more concerned with the reflection properties and the transmission properties, film thickness, solar cells, and all those applications. We have got different types of attachments and accessories that can be used for all these type of applications along with the UV visible spectrophotometer. And academic applications, of course, students, you are all using all this. And general type of samples, UV you can use, analyze liquid samples and solid samples. Gas analysis is not possible, which can be done by IR. IR, liquid, solid, and gas, all the three types of samples can be analyzed. But in UV, you can analyze only liquids and solids. And liquids also can be classified into three different groups. One is transparent liquid. Transparent liquid means pure water is 100% transparent. Acetone, methanol, these are all transparent liquids. You can directly measure the absorbance value. You don't require an attachment. But the sample is a little turbid sample. It's a turbid liquid. It's a very hazy liquid. Then you cannot measure the absorbance directly. You require an attachment called integrating sphere. And using this integrating sphere, you can measure the transmittance value or the reflectance value of the turbid sample. And it can be an opaque liquid. Opaque liquid means highly colored samples. Blue color liquid or highly dark color, black color liquid, red color liquid. Light cannot pass through because the color is so dark. They are almost opaque liquid. Then again, you require an integrating sphere, and you can do only reflectance measurements for opaque liquid. Similarly, solids can be a powder, it can be a coating on a glass, or it can be a mirrored surface. Again, you require attachments like integrating sphere, specular reflectance attachment. There are different types of attachments that can be used for the measurement of solid samples by UV visible. Reflectance applications will include color analysis, reflectance properties of coatings on architectural glass, coating on a spectacle, physical characteristics of mirrors, chemical composition of a powder. So these type of analysis can be done. Two main types of component reflectance. When you say reflectance, there is a component called specular reflectance. There is another reflectance called diffuse reflectance. What is the difference between these two? Specular reflectance means a light is coming and falling on a very shiny and smooth surface, even surface, and it is getting reflected from the surface. Angle of incidence is equal to angle of reflection. That is called specular reflectance. So in specular reflectance, your angle of incidence is equal to angle of reflection. But in diffuse reflectance, the surface is not a very smooth surface. It is a very rough surface. It's a structured surface. It can be a powder sample. So in that case, the light will go inside the material, and while coming out, the light can come out in different directions. And that is what is known as diffuse reflectance. To capture all these diffuse reflectance rays, you require an integrating sphere. Okay. So specular reflectance can be studied, diffuse reflectance can be studied, and the total reflectance, absolute reflectance can be studied using these attachments. Okay, this we have already. Then chemical reaction complex, and sometimes you can add certain derivatives, reagents to a sample, and the reagents will react to certain component, and then that will increase that. For example, I can give an example. In water sample, there is iron and nickel, both metals are present. Okay, so now I want to specifically study what is the nickel content in water. Nickel is a metal, iron is also a metal. They will not directly absorb UV radiation. But I want to quantify nickel content or iron content in water. So now in this case, I want to quantify only nickel. So how nickel can be quantified by UV? Nickel is a metal, it will not absorb UV radiation. I am adding a reagent, dimethyl glyoxime reagent. And this reagent will react with nickel and will produce a complex. Nickel dimethyl glyoxime complex will be formed. And this complex has got absorbance in UV. And with the absorbance of this complex, we can calculate, we can get the actual content of nickel in water. Similarly, if I want to find out iron, I will use a different reagent which will react only with iron and form a complex. And from the absorbance of that complex, I can find out what is the content of iron. So this is nothing but a complexation reaction method whereby even metallic contents can be quantified by UV after formation of a suitable complex with a suitable reagent. And this is normally done in water analysis. Okay. So if your sample is absorbing, no problem. You can analyze the sample directly. But if the sample is non-absorbing, for example, water, this is what I have shown you now, iron and nickel. I want to find out cations and anions in my water. I want to find out nickel content, iron content, what is the content of phosphate, how much is chloride is there. And there are other methods. If I want to find out metals in water, I can go to atomic absorption. I can use an ICP, but they are all very costly equipments. Whereas UV is a very low, what you call much more economical equipment. But UV cannot detect directly metals or non-metals. I cannot directly find out iron or nickel or magnesium in my water content, in my water sample. Then I am using whatever I have shown you I am adding some reagents, and these reagents are selective reagents, and they will react with a certain metal only, or a metal or a non-metal, and from the and they form a complex, and from the absorbance of the complex, we can find out what is the content of my metal or a non-metal in water. And these applications are very important in some of the major petrochemical industries, fertilizer companies, thermal power generation companies, because they use huge amount of water in boilers and cooling tower. And boilers and all, they are converting water into steam, and the steam is getting circulated in the manufacturing plant. And during the course of circulation, they pick up a lot of metal and non-metal impurities. And if the metal content increases, there will be coating inside the boiler. And this coating, that is what is known as crust formation. And if too much of crust formation is that there's a safety hazard. The boiler even can explode. So they want to continuously monitor the metal content and non-metal content in water, where we are providing the solution. And we have got a dedicated UV for that, 1280 model, which can be used only for water analysis. And all the reagents are also we are supplying. And these are analysis of non-absorbing sample. For example, if I want to find out what is iron content in water, there is a separate reagent, 110 phenanthrolene reagent, which will react only with iron, and we can find out what is the iron content in water. Similarly, for reagents for metals and non-metals, both are available. Okay. And the last 1 or 2 slides, you should also understand what is a single beam equipment and what is a double beam equipment. Today, everyone prefers a double beam equipment. Nobody wants a single beam equipment. Okay. Single beam equipment means there is a light source. The light is coming from the light source to the monochromator, and whatever is coming out of the monochromator will pass to the sample compartment, and the light that is coming from the sample compartment will directly go to the detector. Detector will give an electrical signal that will be processed by your PCN software. Okay, now that is single beam. There's only one beam. Whereas in double beam, whatever light is coming from the source, it is coming to the monochromator, and whatever is coming out of the monochromator will be divided into 2 parts. One is called the reference beam and one is called a sample beam. And then the reference will pass through the reference side, and the other light beam will pass through sample side. So whatever is coming from the reference and whatever is coming from the sample side can be again, it will be passing through either through 2 different detectors, or you can combine these 2 beams with the help of a chopper, and it can pass a single detector, and finally it will go to the signal processor. So that is a double beam again. So there are 2 light beams in the equipment. And what are the advantages and disadvantages? Single beam system, high energy throughput, fewer moving parts, instrument is less expensive, but the major disadvantage is unstable. Unstable baseline, no reference correction. Whereas for a double beam system, advantages are more sensitive, more stable. There will be corrections for fluctuations in voltages or whatever it is. And disadvantages is slightly more expensive and more electronics and moving parts. But today, every user will prefer a double beam system over a single beam system. So most of our equipments, what we are offering, they are all double beam systems. We have got only a single beam, only one model, which is a single beam system 1280, which we are promoting for water analysis. But all other applications in the pharmaceutical industry, all other requirements, we are promoting our double beam system. So we have got all double beam systems only. Okay. And then this is the last slide. Do's and don'ts, especially students have to be very careful. You are using sample cuvettes. And number 1, don't use a glass cuvette in the UV region. You will get continuously fluctuating readings. You have to use only a quartz cuvette. And if you are measuring in visible region, you can use both, no problem. And dry the cuvettes completely. After the use of the cuvette, you have to clean the cuvette well with water and some solvent, and see that all the sides of where the cuvette is very, very clean. And if there is some residue still remaining after the cleaning, what you can do on an evening, you can put it in weak chromic acid solution, or even you can put in dilute nitric acid solution, keep it overnight, and they are all very, very strong oxidizing agents. Next day when you come, you take it out, clean with plenty of water, rinse with distilled water, and finally rinse with pure quality acetone. Your cuvettes will be extremely clear. And after cleaning, never dry the cuvette in an oven. And these people are committing this mistake even in industry. If you are keeping the cuvette in an oven, there will be changes in the path length that will affect your quantitative analysis. Never ever dry the cuvette in an oven. Just clean it, rinse with pure quality acetone, just keep it on the table for 5 minutes. It will automatically natural dry. Okay, so that's it. So, and then when you are starting the equipment, when you are switching on the equipment, see that nothing is there inside the sample compartment. If some cuvette is there, please remove it. Ensure that nothing is kept in the sample compartment when you are switching on the equipment. Once you switch on the equipment, it will undergo a self-check, which takes hardly about 5 to 10 minutes time. It will check everything, and if there is any problem, it will indicate. So before doing that, you must see that nothing is there inside the sample compartment. And dust is a main enemy of any electronic equipment. Dust is the main enemy. See that your instrument is kept in a very clean environment. If you want, at the time of leaving the lab, you can even cover it with a cloth or something, cover or something, if you want. Okay. And when the measurement is going on, when the instrument is initializing, as I told you, when you switch on the instrument, it will undergo a self-initialization step, which takes about 10 minutes time. When this initialization is going on, don't open the sample compartment cover. Okay. And second point, another point we have to keep in mind, when you are cleaning the cuvette, after cleaning, after taking the sample solution, you have to wipe the sides down with your apron or your lab coat or rough. You have to use a very smooth tissue paper, because if you are using any rough surface, it will create small scratches on the surface. Okay. And so these are the do's and don'ts one has to always keep in mind. Otherwise, UV is a very simple equipment, very easy equipment, very user-friendly software, and it has got tremendous applications in. So as pharmacy students, you can have so many different applications for UV in your laboratory. Okay. And that was the last slide. And this is my contact details, my email ID and mobile number. If anybody wants to contact me in future also for any sort of requirements, you can always contact me. You can talk to me. You can send me an email, and I'm available. Okay. So with this, I finished this small discussion on UV, and I hope I was able to put across some basic information to all the students. And if you are able to, at least these are the things which are essentially required. You should understand, so that tomorrow when you are going out of your university or college, when you enter the corporate world, as I told you in the beginning, you will be self-sufficient in handling the equipment, making use of the equipment to the maximum fullest extent. And that's all the purpose of carrying out of these type of seminars or webinars. And is only to give you the basic ideas, the fundamentals that will only help you in handling the equipment and make you more comfortable with the usage of the equipment. So thank you very much for giving me attention for the last 2 hours. And if any question is there, I will try to answer that. Over to you.
स्टूडेंट्स कोई क्वेश्चंस हैं आपको रिगार्डिंग द यूवी स्पेक्ट्रोफोटोमेट्रिक टुडे ट्रेनिंग प्रोग्राम? अपना माइक आप अनम्यूट कर सकते हैं, क्वेश्चंस पूछ सकते हैं. Seventh sem students, are you there?
Sir, these students are using a UV spectrophotometer in the lab, sir?
Sir, right now they are not using because they are offline mode is currently चालू. पहले
Okay.
जो मोड ऑनलाइन था सर, तो उस पे तो पॉसिबल नहीं हो पाया.
हाँ. But UV spectrophotometer is there available in the lab.
Yes, sir, available.
Okay. I think then they can start using when the actual session starts. Now I think the pandemic is almost getting over. Sure. I think all institutions are slowly opening up.
Slowly. College open हो चुका है sir.
Yeah, correct. Industries are all opening up. All institutions are all opening up now. And because of this pandemic only, I was doing a lot of online programs for students across the country. But I still feel, sir, effect will be more when we actually come to your place and do this in your seminar hall, facing the participants and students. That will be my experience shows that will be more effective than conducting a program online.
Yes, sir. Yes.
This is my personal opinion.
Yes, sir.
नया लागत था, नया अरे सुअर था, देख कलियां लेके आए.
Hello.
Yes, sir. I think there are no questions
Any
come to the
questions?
students.
Okay. So, sir, thank you so much, sir, for giving today also so beautiful and so nice session. Also, बच्चों के बहुत knowledgeable था, especially 7th sem student जो RGB से related है हमारे यहाँ. They have also syllabus में है उनके courses UV spectrophotometric training. तो
Okay.
मैं समझता हूँ कि जिन बच्चों ने भी आज किया होगा ऑनलाइन तो डेफिनेटली उनको रीड करने में और आसानी जाएगी और नाउ जब हम प्रैक्टिकली लैब में परफॉर्म करेंगे तो ज्यादा बेटर ढंग से और वो समझ पाएंगे और इजीली तो पूरी चीज को समझ पाएंगे आपके लिए.
Yes, sir. Yes, sir. Yes, sir.
तो सर थैंक यू सो मच सर. गिरिजन सर.
Yes, sir. My pleasure, sir. My pleasure. Anytime you want any help from my side, please do contact me, sir.
Thank you, Toshvin Analytical Private Limited, Mumbai. And thanks to Innoval Academic Society, Dr. Sumit Dwivedi. And thanks to Dr. Ashish Jain, Principal MCP. And thanks Rahul sir and Manu Priya. And thanks to all students for listening carefully and silently. And if any doubt, you can contact also again, sir. Sir is giving number there. You can also contact. और सर हम रिक्वेस्ट करेंगे कि whenever possible physical form में हम इसको कर पाए इसको तो बच्चे ज्यादा बेटर ढंग से
Yes, sir. I also prefer that, sir. मुझे भी और पसंद होएगा.
जी जी सर.
So I hope to come to your place once, sir, in Bob.
बिल्कुल सर. I will invite you, sir, whenever possible.
Thank you, sir. Thank you very much.
So I leave this session, sir. End the session.
Yeah. Okay, sir. Thank you so much, and I wish all the best to the students. All the best.
Thank you so much, sir, for giving